Welcome to a presentation brought to you by the American Wood Council. Thank you for your participation in our webinar today. This webinar is intended to provide general information only and does not constitute professional or engineering advice. Please note that this webinar is being recorded, and by remaining a participant, you automatically consent to such recordings. If you do not consent to being recorded, please disconnect from the session. This presentation is worth 1 LU HSW with the AIA and 0.1 credits with the ICC. To receive credit for the course, you must attend this webinar for a minimum of 50 minutes. At the end of 50 minutes, you will see your certificate appear on your webinar console. Your certificate will also be uploaded into your learner profile on learn.awc.org, provided you registered for today's webinar with the same email address as your account profile. At the end of today's session, our presenter will have a live Q&A with the audience. Please input your questions into the Q&A panel throughout the session. And now, for today's presentation.
Hello, everyone, and welcome to American Wood Council's webinar on ISO 13391, Advancing Carbon Quantification for Wood Products, a new framework for reporting forest and wood product greenhouse gas dynamics. My name is Sarah Pulls. I'm the Manager of Sustainability Standards at AWC, and I am excited to be talking to you all today about the new ISO standard for quantifying wood product greenhouse gas dynamics. If you're not familiar with AWC, welcome. We are the nationally recognized technical authority and advocate for the sustainable wood building products industry in codes, standards, legislative, regulatory, and climate policy arenas, representing around 86% of the structural wood products industry. So this course is going to be a bit unique. We're going to take a slight break from our more typical engineering and codes-focused webinars and talk about a new sustainability standard, that is ISO 13391. This standard was published earlier this year. It specifies how to calculate greenhouse gas dynamics for a set of wood and wood-based products, including 4 components. And those components are the value chain emissions associated with the products, the carbon stored in those products, the carbon balance of the forest associated with the products, and the potentially displaced emissions from using wood products in place of higher emission materials. In this course, we'll start with some wood product greenhouse gas accounting basics, go over what each of those 4 components is and how they're calculated according to ISO 13391, and talk about how wood products, with the help of ISO 13391, can contribute to climate solutions. By the end of the course, you should be able to understand how wood products can contribute to reducing carbon in the built environment, recognize the importance of consistent and science-based greenhouse gas reporting, be familiar with ISO 13391 and its approach to quantifying GHG dynamics, and explore how ISO 13391 can support wood sector greenhouse gas reporting and climate-forward design. I have tried to make this fairly accessible to folks without a sustainability background. Maybe you're coming from the architect world or the engineering world. So I'm going to start out with some basics so that we're all sort of speaking the same language, and then get on to the standard. And with that, we'll dive right in. So like I said, we're going to start out with some basic terms and definitions. These may seem fairly simple, but it is really important when you're talking about pretty technical things that everybody is using the same words to mean the same things. So we'll start out with some terms around carbon flows in and out of the atmosphere. Like I said, some of these terms might seem pretty straightforward, but people misuse these words all the time. And when you start adding layers of complexity, they can get confusing. So the first two, greenhouse gas emission and greenhouse gas removal, are a release and a withdrawal of an amount of greenhouse gas to or from the atmosphere. So if you drive your car, you burn gas, carbon dioxide goes into the atmosphere, that's an emission. If you grow a tree, the tree photosynthesizes and turns carbon in the atmosphere into sugars, that's a removal. These two are active fluxes. So kind of imagine that there's this area that's atmosphere, and then there's this area that's not atmosphere. And what we, from a climate perspective, what we really care about is greenhouse gases crossing over that line from the atmosphere to not the atmosphere, and from not the atmosphere to the atmosphere. So these two, emissions and removals, are active fluxes. So they result in a change in the amount of greenhouse gas that's in the atmosphere, either putting more in the case of the emission, or taking more out in the case of the removal. Carbon storage is when a material like wood in your house, or wood in a tree, or plant matter in another plant stores carbon that has already been removed from the atmosphere. So if you look around you right now, maybe your desk is made of wood. That desk is storing carbon. It's not currently coming in or out of the atmosphere, so it's not having a direct effect on climate. But the fact that it's in your desk means that it got removed from the atmosphere in the past, and it's not currently going into the atmosphere. So it is a positive thing for climate for that carbon to stay in your desk, but it's not an active emission or removal. The next two terms that I want to talk about are biogenic and fossil carbon. Fossil carbon is pretty simple. It's carbon contained in fossilized material. When you burn fossil fuels, you take carbon from fossil reserves and emit it to the atmosphere. And generally speaking, those reserves are not replenished. Biogenic carbon is carbon derived from biological material, excluding fossilized materials, such as from trees and other plants. And what makes biogenic carbon different from fossil carbon is that biogenic carbon stocks are able to be renewed within a human timescale. So right now, as we speak across the planet, you have both biogenic emissions and biogenic removals going on. And from a greenhouse gas accounting standpoint, it's important to look at these two things separately because they have different or distinct impacts on the climate. And then I also just want to note that these words on the slide now can be combined with the words on the last slide. So for example, you can have fossil carbon emissions, you can have biogenic carbon removals, you can have biogenic carbon storage. So you can mix and match these things as appropriate. So next we'll go over wood product sustainability and how wood products can contribute to reducing carbon in buildings. Two main goals that were put forth by the UN Framework Convention on Climate Change, the UNFCCC, are to reduce greenhouse gas emissions and enhance greenhouse gas sinks. Basically put less greenhouse gas in the atmosphere and pull more out. Wood products can contribute to both of these goals. This is a fairly unique quality of wood products and opportunity. Probably the first contribution that most people associate with the forest sector is enhancing forest carbon stocks. So having more carbon in the forest. But in addition to that, wood products can also help to enhance the carbon stocks in the wood product pool, such as being stored in the built environment. And they can also help us reduce emissions from the building sector by providing lower emission materials to use in place of higher emission materials such as steel and concrete. So on that goal of enhancing forest carbon stocks, forests in the US actually provide a huge service for climate change mitigation. Every year, the amount of carbon stored in our forests increases, resulting in a net removal of carbon from the atmosphere. So that means that every year there is more growth in US forests than there is harvest and decay. In 2023, which is the most recent reporting year, US forests had a net removal of around 886 million metric tons of carbon dioxide equivalents. And to put that into perspective, that's equivalent to around 14% of gross US emissions. So the removals from the net growth in US forests were equivalent to around 14% of gross US emissions. And if we want to maintain this net growth, we want this removals quality to continue into the future, we need to have healthy forests, which means arming our forests against threats like wildfire, pest outbreaks, disease, and drought. When you have forests that are overstocked, they are stressed and they tend to not be resilient when threats come along like wildfire, drought, pests, etc. So forests that are at healthy stocking levels are much more likely to succeed against these threats. So harvesting wood can actually help to promote resilience against these threats, for example, by reducing fuel loads that increase risk of wildfire, or another example, by maintaining healthy stocking levels to reduce stress on the forest. And while it may sound a bit counterintuitive, wood products also help to prevent deforestation. So this is less about enhancing forest carbon stocks, but about maintaining the land area of forests so that forest carbon stocks are not declining because of deforestation. So maintaining a strong market for wood products helps to incentivize landowners to keep their forest land as forest land, and prevents that land from being converted to other uses like agriculture and development. So in the US, we have a lot of pressure on land to become agriculture, become development, be forestry, and having a market for wood products that gives people a financial ability to keep that land as forests is really important to preventing that land conversion to other uses from forests. So this graph shows forest area in the US over the last 180 years. And you can see that forest area declined in the 1800s as people cleared land for agriculture and development. But since the early 1900s, the area of forest land in the US has remained relatively stable. At the same time, the US population has increased dramatically, which speaks to our ability to manage forest land so that this area can be maintained even as we're supporting a growing population. In the same way that forest carbon stocks are increasing over time, carbon stocks in the wood product pool, such as the built environment, are also increasing. Wood is approximately 50% carbon. So all wood that's in use in our buildings, in our homes, in our furniture is storing carbon. And as we add more products to that pool, that storage increases. In 2023, the net accumulation in the wood product pool was around 91 million metric tons of carbon dioxide equivalents, which is equivalent to around 1% of gross US emissions. And the more wood we use, particularly in products with long lifespans, such as housing and buildings, the more this pool will grow. So then the second UNFCCC goal was to reduce emissions. So we had enhance stocks and then reduce emissions. And wood can also help us reduce our embodied emissions by providing a low emission alternative material to use in place of high emission materials like steel and concrete. As an example, a meta-analysis of 21 studies found that on average, for every ton of additional carbon in construction wood products that are used, you could see 2.1 tons of carbon in emission reductions. And that can add up to significant embodied carbon reductions across a project or if implemented at larger scales. Pictured below are a few of AWC's wood product EPDs, and EPDs can provide the data needed to understand the possible emission reductions that could be achieved by switching to a more wood-inclusive design. Now, I've covered some of the main ways that wood products can contribute to reducing carbon in the building sector. But it's important that when we're quantifying and communicating these benefits, it's done in a robust and science-based way, which requires us to have a good understanding of the processes that are involved in this accounting. This on the slide is a diagram of the carbon cycle of working forests. So on the right, you have a forest that's growing and decaying. Trees are harvested from the forest to provide timber for wood products, and then new trees are planted or grow in place of the old ones. As we move to the left on the diagram, wood products are produced and stored in carbon while in use, and then at least some of that carbon is emitted back to the atmosphere at end of life. This cycle is pretty complicated, and you've got different numbers that you can quantify. So over here we have removals as the forest grows. And then we have emissions from forest decay, wood product production, and wood product decay. Some of those emissions are biogenic, and some of them are fossil emissions. And then we also have carbon storage, both in the product and in the forest. And finally, we have emissions that were potentially avoided by using wood in place of higher emission materials. Because this cycle is so complex, it's difficult to know how each of these factors should be quantified and communicated so that we're ensuring accurate information is presented. And so ISO 13391 was developed to provide a standardized and consensus-based approach to quantifying the greenhouse gas dynamics associated with wood products. So at this point, you've heard me say ISO 13391 like 5 or 6 times. What exactly is ISO 13391? It is a series of standards, ISO standards, that specify how to calculate the greenhouse gas dynamics for a set of wood and wood-based products. It's intended to be used at an organizational or other aggregate level, and I'll explain that more in the next slide. And as I mentioned at the beginning, it covers 4 components. So these are the value chain emissions, the harvested wood product carbon, the forest carbon, and the potential displacement. So who uses this standard? The standard is meant to be used by organizations or associations that produce wood products or are forest landowners. So a user could be a single company, or it could be a set of companies, such as an association. It could also potentially be used by a jurisdiction, like if a state wanted to understand the greenhouse gas dynamics associated with their forests and wood products, they could use the standard to understand those dynamics. When the standard is used by an organization, they are required to include all of the wood products placed on the market by that organization. So it can't be done just for a subset of products made by a company. The idea is to understand the entire impact of that company producing wood products or managing forest land. And it's not just limited to structural wood products. It refers to wood and wood-based products. So that includes structural wood products, but also things like pulp and paper products, non-structural wood products, as well as wood-based bioenergy. These standards were developed by the International Organization for Standardization, or ISO, which is an international non-governmental standards development organization founded in 1947. They develop standards on a wide variety of topics. They have over 800 committees and subcommittees that, through the participation of 173 countries, have developed nearly 26,000 standards and technical documents. Their key principles include responding to a market need, developing standards through a multi-stakeholder process, basing standards on global expert opinion, and basing standards on consensus. Among the standards that ISO has developed are a few really keystone environmental standards. These include ISO 14040 and 14044, which set out the core rules for how you do life cycle assessments. So these documents are the basis for how all LCAs are done across all sectors and across the world. ISO 14025, which sets the rules for environmental product declarations, or EPDs. And again, all EPDs have to adhere to ISO 14025. So these are really core base standards. And then also ISO 21930, which is the standard that we at AWC, as well as others internationally, follow for construction product EPDs. And just to clarify the hierarchy, ISO 21930 follows ISO 14025. So these, as you keep going in sort of level of specificity, you're creating this framework that's based on families and groups of ISO standards. The ISO development process is based heavily on international consensus. So the idea is that you have all of these countries coming together to develop this standard representing various stakeholder interests within their country, and then working together to jointly develop this standard. It's an iterative process that involves multiple rounds of comments from experts and then comment resolutions, and involves all of the countries that are interested in that standard. So the ISO 13391 series was developed according to this process over a period of nearly 4 years. There were 39 countries and 11 additional organizational liaisons involved. There were 71 experts on the working group where the standard was developed, and a total of 8 drafts were produced before it was finally published. And all of this is just to demonstrate that, the standard wasn't developed overnight. It is the result of many rounds of drafting and comments and revision and drafting and comments and revision. There were a lot of people at the table whose perspectives were taken into consideration when the standard was being developed. And it is really a product of this development process and this consensus process. And when this standard was being developed, the folks in the room did not want to just start from scratch. This needed to be a credible standard, and so it needed to stand on some existing guidance that had credibility to it. And so the methodology and the standard was largely based on the methodology used by the IPCC and the IPCC guidance, which is the guidance used globally to estimate country greenhouse gas inventories, for example, for reporting to the UNFCCC under the Paris Agreement. This is important because it really speaks to the credibility of the methodology used. Not only was it developed through a rigorous consensus-based process, but it was adapted from methodology developed by the world's leading authority on climate change and emissions reporting. The series consists of 3 standards. The first standard covers the general framework, as well as the value chain emissions and harvested wood product carbon. The second standard covers the forest carbon balance, and the third standard covers displacement. There are also 2 related technical reports, which contain guidance, no requirements, but just helpful information for how to do these calculations, and supporting examples for calculating the harvested wood product carbon contribution and calculating the potential displacement. And then there is a third technical report that is currently in development that, if published, will provide guidance and supporting examples for calculating the forest carbon balance. So you've got 3 main standards that cover your 4 components, as well as setting up a general framework for this reporting. And then you've got a few additional technical reports that offer technical guidance in how to do these calculations. I'm going to spend some time going over each of the components, what they are, and how they're calculated. And it's important to keep in mind that each of these components is calculated and reported separately. So we talked before about how there's all of these different things that are quantifiable going on in the forest and wood products carbon cycle. And it's really important that we are reporting what each of these is in order to ensure transparency and allow credibility, because numbers that aren't necessarily comparable are not combined and presented as if they are comparable. So we'll start with the value chain emissions. This component is probably the most familiar to you. It's essentially the same as embodied carbon. These are the emissions associated with the production, use, and disposal of a set of products. The standard requires that cradle-to-grave emissions are included. So this means all emissions from the forest management to the end of life of the products have to be included in the value chain emissions calculations. It includes direct and relevant indirect emissions. So this language is pretty consistent with other greenhouse gas reporting standards in ISO. And it provides criteria to help you determine which indirect emissions are relevant. The user is also required to report and justify any excluded emissions. And then site-specific data is required for industrial processes where the organization has financial or operational control, but then those data can be averaged across sites for reporting purposes. For recycled fiber, upstream emissions are excluded. So the emissions from like the previous iteration of the fiber, but then emissions from the recycling processes are included. And then biogenic carbon dioxide is reported separately from non-biogenic carbon dioxide. And this is pretty consistent with most LCA and greenhouse gas reporting practices. The next component we'll look at is the forest carbon balance. This methodology was adapted from the IPCC methodology to fit an organizational level instead of a country level, which is the level that the IPCC methodology operates at. The IPCC defines 5 forest carbon pools, which are living above ground carbon, living below ground carbon, dead wood, litter, and soil organic matter. So in the diagram, living above ground carbon refers to the carbon in the leaves, stems, branches, etc., everything that is alive and above ground. Below ground carbon refers essentially to roots. Dead wood refers to sticks and logs lying on the ground, as well as to standing dead trees. Litter refers to dead leaves. And soil organic matter refers to organic matter that has broken down to be below a certain size within the soil. These 5 categories are all required to be included in the forest carbon balance. And when you're calculating the forest carbon balance, you're required to have primary or secondary data for the living above ground carbon. So it's pretty common in forestry to base some of the other pools off of data collected from above ground. And this is just due to the ease with which you can collect data on above ground carbon compared to other carbon pools. And generally, there are equations that are pretty robust for associating other carbon pools with above ground carbon. So for example, you wouldn't want to have to dig up trees every time you wanted to estimate the root carbon, because that would be very destructive and also very costly. So you might use an allometric equation to estimate it based on the size of the tree above ground. But to get that initial estimate for the above ground carbon, which is then what you might determine other carbon pools based upon, you need to collect some sort of inventory data for the above ground carbon. And as far as how you calculate the change in carbon of those pools, the standard uses the forest management unit as the basis for these calculations. So because it can be extremely difficult to discern which emissions and removals from forests and other land uses are anthropogenic and which are non-anthropogenic, the IPCC developed a methodology called the managed land proxy. This is where emissions and removals from managed land is considered to be anthropogenic, so human caused, and emissions and removals from unmanaged land is considered non-anthropogenic, so non-human caused. In ISO 13391, the user defines what's called the forest management unit or units where the wood is sourced, and this land is used as the proxy to identify emissions and removals associated with the products under study. So the forest management unit is defined in the standard as the area of forest where wood is sourced for wood-based products, and it's required to correspond with the volume and product mix of the wood products. There's a couple different ways to calculate the forest carbon balance described in the standard. But basically what you're doing is calculating the difference between carbon that was there at the beginning of the study period and carbon that's there at the end. So if you had 100 tons at the beginning and 110 tons at the end, your forest carbon balance is 10 tons. And that positive sign on the forest carbon balance indicates that there was a net removal or a net growth. If you had a net loss, it would be a negative sign. And because you're considering the whole landscape, maybe a landowning company is looking at all of the land they own, or maybe a manufacturer is looking at a sourcing region, you have all of the present age classes represented. So that means that no matter what your time period of interest is, whether that's 1 year or 10 years, you've captured all of the impacts to your forest because you have the accurate age class distribution that's inherently included in your data. The next component we'll look at is the contribution to the harvested wood product pool. So we talked in the beginning of the presentation about how as you add carbon to the harvested wood product pools, for example, the built environment, you're having a net change in carbon that's in that pool. So this component is based on the 6th IPCC carbon pool, but instead of having it just be one pool in the standard, it's split into 2 separate pools. So one for the in-use products and one for the storage from products discarded in landfills. So the in-use wood products pool is required if this component is calculated, and the landfill pool is recommended, which in ISO terms is like a strong suggestion, but it's not required to be included. And this difference here would mostly be used if maybe it wasn't applicable because you don't have very much wood going into landfills in some countries, for example. So wood is approximately 50% carbon. So you can estimate the carbon storage by estimating how much wood is being placed on the market and how long it will last. One of the key parameters in estimating how long it will last is the lifespan of the product. So this table shows the IPCC default lifespans for 3 categories of wood products. And these lifespans are incorporated into the default factors provided in the standard. The contribution calculated in ISO 13391 is the net contribution. So rather than calculating all of the carbon and all of the wood products that a company puts on the market, the focus is on the net addition. So the amount added to the market minus the amount that left the pool in that time period. So let's say there's a wood products producer, and in 2023, they added this much carbon to the market. So this is the old pool. Now they've added some to the market, and now there's this much carbon in the market. But wood products don't just stay in the wood product pool forever. You know, we tear houses down, we throw products away. Some things get burned or go to landfills, and some of that carbon decays. And so this much carbon left the harvested wood product pool in 2023. So in 2023, this net HWP carbon is what will get reported as the contribution for ISO 13391. And this concept is taken from the IPCC methodology, adjusted to the organizational level. And I also want to draw the connection to the way the forest carbon balance is done. In the same way that we look at a forest carbon balance, including what's coming into that forest and what's leaving that forest, and we want to understand the net result of what's coming in and what's leaving. We're doing the same thing for the harvested wood products pool. So we're looking at what's coming into the pool, but also what's leaving the pool, and reporting that net balance. So there are different tiers within the standard to calculate the harvested wood product contribution. Tier 1 uses default factors based on IPCC product lifespans. This is the simplest tier if data are limited. These default factors are multiplied by the amount of wood product carbon added to the market in the study period. So for example, if an organization added 100 tons of sawnwood carbon and 50 tons of paper carbon, 100 times 0.25 is 25 tons, plus 50 times 0.04. The net contribution would be 27 tons of carbon. So this is the most simple way of approaching this if better data are not available. Tier 2 can be used if better data are available for estimating the outflow of carbon from the pool. For example, you might have better data on product lifespans, on recycling rates, on product mix. So this is like where your timber is going. Maybe you have a better breakdown for your roundwood, or on maybe past market growth. And then tier 3 could hypothetically be used if you had primary data for both carbon going into and carbon leaving the pool, but at least to my knowledge, that does not exist today. The estimation of this component is heavily dependent on data for past market inputs, because we're trying to understand not only how much carbon is entering the market, but also how much is leaving it. And to know how much is leaving it, we need to know what is already there. So unlike a forest where we can just walk in and measure the trees and have a pretty good understanding of how much carbon left the forest since the last time we measured it, it's much more difficult to measure for example, the toilet paper that people use and the packaging and the old furniture that they throw away. So we rely on past market data and on lifespan modeling to estimate how long products are likely to last. The last component is the potential displacement. So this is calculated by multiplying the amount of wood products produced by a displacement factor. The displacement factor represents the potentially avoided emissions from alternative products relative to the biogenic carbon in the wood product. So the idea here is that you are replacing a higher emission material, such as steel or concrete for a building sector example, with a wood product which has a lower emission. And by doing that, you are avoiding potential emissions that might have otherwise been emitted. There are conservative default factors that are provided in the standard, ranging from 0.5 to 1.2. Or other factors can be used if they're based on credible sources like LCAs, EPDs, or peer-reviewed research. And it's important to note that while the first 3 components take an attributional approach and estimate emissions and removals that did happen, the potential displacement component estimates emissions that didn't happen but potentially might have happened if conventional materials were used. So to maintain scientific rigor and credibility, each component is calculated and reported separately. And there's a statement describing the limitations and the considerations associated with the potential displacement component that's required to be included in the report if this component is calculated. So now we've gone through the 4 components and some of the technical aspects of the standard. To demonstrate what this quantification and reporting could look like in practice, we can look at the SCA annual report. SCA is a Swedish forest products company. They make a range of wood and wood-based products, including solid wood products, pulp and paper products, and bioenergy. Their annual report was published before ISO 13391 was published, so it does not necessarily follow the standard, but it does use a similar methodology and can serve for our purposes as just an illustrative example of how the standard could potentially be used. This image shows SCA's forest land, which is what they use to calculate their forest carbon balance. In addition to their own forests, they also source wood from upstream forests not owned by SCA. And for those forests, they determined that the carbon stocks were increasing, but chose to exclude them from their estimated forest carbon balance so as not to overestimate their removals. So in this example, SCA determined that their value chain emissions totaled 0.9 million tons of carbon dioxide equivalents. Their forest carbon balance was a positive 5.1 million tons of carbon dioxide equivalents. And again, that positive sign indicates a net removal. So there was more growth than there was decay and harvest. Their wood product contribution was 0.7 million tons of carbon dioxide equivalents, and that indicates a net accumulation of carbon in the wood product carbon stocks. And then they estimated 7.4 million tons of carbon dioxide equivalents in potential displacement. As we wrap up this presentation, I want to zoom out to the main problem that we're facing. The built environment is responsible for over a third of global energy-related carbon emissions, and embodied carbon emissions are projected to continue increasing. The graph on the left shows embodied carbon as a portion of building sector carbon, and it is projected to increase significantly compared to operational carbon. The graph on the right shows embodied carbon from various materials projected to 2060. The materials with the highest emissions are concrete, steel, brick, and aluminum. So generally not a great outlook for the building sector. This is a problem that we need to solve. And if we want to solve this problem, we need to make significant changes to how we design the built environment. The main changes recommended by this UN Environment Program study include improving conventional materials, avoiding waste, and shifting our material use to bio-based materials. But in order to go about this solution effectively, in order to shift to bio-based materials effectively, the decisions that we make need to be informed. And that information has to be grounded in robust methodology such as IPCC methodology. So we need to make sure that we are getting accurate and credible environmental information in order to move forward with changes in the way that we are designing the built environment. And ISO 13391 provides a consensus-based, standardized way to quantify wood sector greenhouse gas dynamics. It can be used for organizational greenhouse gas reporting for organizations that own or manage forest land, as well as for organizations that produce wood products. And it can also be used in research to evaluate a system or other levels besides the organizational level, or to understand the climate impacts of using wood and wood-based products so that we can make decisions and make changes that are based on science and quantifiable information. So hopefully you learned something today about how wood products can contribute to reducing carbon in the built environment, and how ISO 13391 can provide a standardized, consensus-based method to quantify the impacts of using wood. And with that, I will wrap it up and just say thank you so much for your time and attention, and open it up for any questions.